Uh, Good afternoon. Hello, everyone. I recently joined Nicolaus Copernicus University in Toruń, actually last month. So I am pretty much new here, still exploring ways to cope up with things. So today I'll be talking about preventing zero-point energy leakage in classical trajectories. I know it is odd. Don't frown. I'm here to explain. Let's see. So as we all know, zero-point energy is an outcome of quantum uncertainty principle, right? Your classical mechanics does not have any clue what the heck we are talking about. As a result, when you propagate your dynamics classical trajectories, then in a modes your energy may fall below its quantum zero-point energy value. And this leaked energy, if you are talking about an isolated system, this leaked energy will accumulate into some other modes, making it unphysically hot. But normally in quantum dynamics, we don't see this problem. Let's look at some numbers, so give you an idea about how much the energy we are talking about. So benzene, we are talking about 50 kilocal per mole. Nucleobase adenine, very important, as Rafal showed. It is 75 kilocal per mole. Someone is talking about polyaromatic hydrocarbon pH molecule, let's say pyridine, 130 kilocal per mole. So the point is, we are looking at a handsome amount of energy, right? And the problem become more serious if, let's say, you imagine that your several modes leak the zero-point energy and it's accumulate onto a particular bond, so it's making it very, very hot, unrealistically. If your barrier height is comparable to the zero-point energy, you will in a serious trouble. So basically, based on these erroneous energy transfer, a particular reaction channel can be opened up or closed, right? And for long time scale dynamics, as we are interested recently, so this zero-point leakage problem very affect the dynamics very severely. Okay, you have a simplest fix. Always there will be a simplest fix, right? You ignore the zero-point energy. But then after the trajectory, you calculated all the trajectories, you discard the zero-point energy violated trajectories by looking at the individual product, or you sum all the products and you can discard these trajectories. Very simple. But then you are looking at you have to discard a lot of trajectories. For instance, Bowman had to discard 85% of its zero-point energy violated trajectories while simulating the roaming reaction of acetaldehyde. And nowadays, we are not very proud of doing such type of computational waste, right? Because we are now very much well aware of carbon footprint emission. So there are other methods called active methods. Here we directly intervene into this classical propagation by putting some constraint, and this problem is not new. You can see that people are trying for a long time and giving some prescription to tackle this problem. Most of the prescriptions involved work in the normal mode coordinates, meaning you need to calculate Hessian during the propagation. And certainly, we don't want to do that because I cannot afford Hessian calculation in my ab initio molecular dynamics trajectories, right? So I want a Hessian-free method, simple. I always work with simple things, right? So simple and general enough so that I can integrate with any classical trajectory propagator. By the way, there is a good model, a good method, similar what Daniel was speaking the other day, quantum thermal bath model by these color noise Lagevre dynamics. They, on the fly, they tune the system bath coupling parameter by quantum fluctuation dissipation theorem. You know much better than me. And then each vibrational mode is effectively thermalized to these appropriate zero-point energy value. Okay. If you can afford it, please do. But I'm not sure how well it will be working on excited states. There are no work. But if you are happy with ground state, if you can afford this type of dynamics, you are welcome. It should work pretty well. So now I present my local pair zero-point energy correction method. The main point is Hessian calculation during the trajectory is not needed anymore. So the idea is you monitor the local stretching vibration. Whenever the kinetic energy of the local stretching vibration drops below a certain threshold, in that case the ZPE value, then you pumped some energy, the particular amount of energy which is the leaked energy into that specific bond. And of course, to compensate, you have to add this added energy you taken out from the other local pairs, construct the energy pool, right? So you immediately guess that it will inspired by the Lowe-Anderson thermostat model. But instead of receiving energy from the thermal bath, the energy is taken out from the molecule itself. So making it inherently energy conserving and as a microcanonical ensemble. And all the energy adjustments are doing in the nuclear velocities, only in the parallel direction. So it acts as a central force problem. As a result, it conserves the linear and angular momentum by construction. Let's take an example how it works. Let's take this water dimer. In this case, my system of interest is water dimer. See, very simple. What can be more simpler than water? So we are looking at high frequency normal modes of water dimer can be represented by the 4 OH local stretching vibrations, and basically they are very much prone to zero-point energy leakage because of high frequency, you know. So I will monitor these 4 OH stretching modes. Let's rename them AH local pairs to understand the protocol. And all the other atom pairs, not necessarily bonded, can act as the spectator mode, not spectator, energy donor mode, who construct the energy pool. So we have total 11 local pairs. Let's rename them BC. And then at the beginning of the dynamics, you average the parallel component of the kinetic energy for each AH local pair, right, for a certain period of time. Now you have to be a little bit careful because these are the system parameter. You need to adjust a little bit. But the point is you should allow these local vibrations to complete a few oscillations so that you can gather the energy and call it your reference zero-point energy value. This value is your reference value because at the very beginning of the dynamics, we will not expect much zero-point energy leakage. Okay, then after a later time, this is my correction checking time. I calculate exactly the same thing for the same time duration, and then I compare. If my leakage exceeds more than my predefined threshold, I apply this correction. So here in blue, I will add the exact amount of energy in of course in velocity terms to the AH local pair, and I subtract the same amount of energy by all the BC local pairs. This F is actually a weight factor which determines that, okay, if which BC local pair has much energy, it will donate more to the energy pool. Okay, so my stage is set now, and it's time to apply. I will do, as I said, ground state, Born-Oppenheimer molecular dynamics of water dimer. The point to be noted is the stretching mode that caused the dimer to dissociate is around 200 wave number, right? So the ZP is 0.012, and the dimer dissociation energy is 0.225. So this mode cannot have no way to surmount this energy unless it will receive some leaked energy from the other local pairs. Okay. So now in this slide you are seeing this is the OO distance, that is the oxygen distance. These are the oxygen of monomer of the dimer. If you do not, if you do nothing, you will see your dimer will explode after 5 picosecond. But with our method, I can hold the dimer for a longer period of time. Basically, these gray lines are individual trajectories, and these blue and red lines are averaged. In this case, if I remember correctly, 100 trajectories involved. Bowman did exactly the similar calculation and also had to apply some constraint to keep the dimer on hold. But Bowman applied a very small time step and also corrected very frequently compared to my case. Because as I told you, they are applying these momentum sign change of momentum, which will be very noisy. And the more important thing, I do not require any Hessian. Recently, Truller modified our method 2 months back, I guess. So the basic idea is exactly the protocol is the same, but instead of doing a brute force energy conservation, that is in my case, they construct a cost function incorporating the energy pumping and reducing equation. And then they optimize it to do the kinetic energy redistribution. These are the two pseudocode presented in Truller's paper. Okay, so to conclude, I present a Hessian-free method to prevent zero-point energy leakage in classical dynamics. It is very general in nature and more importantly, readily extendable to excited states also, because you only need nuclear velocities, nothing more. A standalone photon module is in the GitHub. You can check it out and you can integrate to any of your classical propagator. But we did your work a little bit simpler. In Nutanix, our software, we already implemented it inside the code. Before concluding, sorry, Sandra, I just couldn't refrain myself from showing this slide as Sandra was showing. I actually do non-adiabatic molecular dynamics. My research interest in non-adiabatic molecular dynamics. I more or less do the same thing as Marianne was saying, Sandra was saying. And this is my take on this same cyclobutanol dynamics, where Sandra proposed a time scale of S2 lifetime is less than 300 to 500 femtosecond, I guess. Our prediction is 9 picosecond. So see how widely different is this. Let's wait for the experiment. And a little bit of advertisement. Recently, I submitted an Opus proposal to develop this machine learning non-adiabatic molecular dynamics. I'll be very happy if anyone is interested, and please let me know, because in Toruń, we really need some manpower and workforce. Thank you. I should thank Mario, because this work I was presenting was done in France while I'm doing postdoc with Mario for 5 years. And of course, the Center of Excellence in Toruń, the reason why I'm being here. Thank you. Thank you all.
Thank you very much. Great talk. Yeah, we have questions. Okay.
I guess that this zero-point energy leaking has some effect in the activation barriers when you have any kind of reaction. So my question is, do you have an idea of how much it can affect this activation barrier? Because in some cases you have critical values just to see if the reaction is going to proceed or not, because the height of the barrier.
Exactly, I understand your question. That is I'm talking about, that if your zero-point energy and your barrier height is comparable, then if leakage happens, you will not cross the barrier. So it depends on molecule to molecule. So you cannot pick a number that, okay, this should be my number to check the zero-point energy leakage. But again, the main thing is the time scale. If you are looking at very ultra-fast time scale, I think zero-point energy leakage doesn't matter. But if you are looking at long time scale, it will surely matter.
Thanks.
So thanks for the great talk. So I'm very confused by all of this. I've thought about it a little bit, but then, so how can you source the zero-point energy? Because you really have, in order to do that, you need to look at the different Hessians in the different bonds that are made. So for an example would be that if I take a very large molecule, then eventually my zero-point energy will be basically infinite, right? But it doesn't necessarily help reactions proceed. In this sense, it doesn't mean that every reaction proceeds.
I understand your question, but the motivation is normally we do excited state molecular dynamics. So let's talk about ground state dynamics. We prepare our initial conditions to mimic the quantum wave packet. How? We put the 0 point energy in each mode by calculating the ground state frequency and everything. And then I am tracking this 0 point energy of each mode.
So the 0 point energy will shift, and this is the energy that you can source.
Yes, you can in during the propagation, but no, if you want to track it on the propagation, then you will again go back to your Hessian calculation. You cannot do that by this thing. Here, we are assuming that okay, my reference 0 point energy will be fixed, but it will change in excited state. But during the course, you cannot change it. It is your reference value.
Okay, thanks.
Thanks for the talk. So I'm a little confused about how you're determining the reference 0 point energy, where you're tracking at the beginning you set some period of time.
Yes.
Where you
The kinetic energy. So we are saying that the kinetic energy itself is the reference value during an oscillation.
Right. But I guess because you're sampling the initial conditions essentially randomly from your quantum harmonic oscillator, right?
Yes.
The 0 point.
But
you will have a normal mode of a certain 0 point energy, but the individual sampling that you get will always be a little different, right? Because you're sampling it randomly.
No, I sample it randomly. Then after the sampling, you put the exact 0 point energy in each normal mode. I don't understand the drama of what you are talking about. So you are putting the, let's say, stretching. So you are putting the 0 point energy of that stretching mode by Wigner distributions or sampling.
Yeah, but so on average, right? But when you sample it from a Gaussian distribution, essentially, right?
Yes.
You will not get exact 0 point energy value, right? Because the momenta and positions are independent.
But at the end of the day, when you sample and you prepare your wave packet, then if you calculate, of course, as an average, then it will be the 0 point energy value. And you can also restrict your by rescaling the anharmonic factor. You restrict your total energy exactly at the 0 point energy value. In this case, I think 1.26 eV. I restrict all my initial conditions having exactly 1.26 eV value. And this 1.26, that is the GPE of the total system, I divided into each normal modes.
Okay, final question.
So I have many questions about this discussion.
I don't know whether the chair is allowed for many questions, but I will be happy to answer.
No, so maybe we can talk during the break. But I wanted to ask something else. So you mentioned that you can use this in the excited state dynamics
Yes.
as well. Did you actually do it?
I didn't do, but I know some people are trying. Some other groups are trying to do it. But Truller also proposed that they are doing it.
And do you expect to see it relevant in some systems? Usually the time scale is much shorter for like the relaxation on the excited states is usually much faster.
Much faster, yes. So then in that time scale, the thing is you can say that okay, while I am in excited states, my parameters will be different. And when I'm ground state, my parameters will be different. It will be in input. And if you see not much leakage in excited states, okay, you are happy to go.
Okay, thank you.
Okay, I think it's time for lunch now. Let's thank the
I
speaker
will not
again.
restrain everybody.
And all the speakers from this session.